Hello students, welcome to IIT PAL Mathematics problem solving session. This is lecture number 5. In this lecture, I will solve some more interesting problems related to system of linear equations. So let's start with problem number 1. Question: let S be the set of all column matrices B1, B2, B3 such that B1, B2, B3 they are real numbers and the system of equations in real variables minus x plus 2i plus 5z is equals to b1, 2x minus 4y plus 3z is equals to b2, x minus 2i plus 2z equals to b3 has at least one solution. Okay, then which of the following systems in real variables have at least one solution for each B1, B2, B3 belongs to S. The first system is x plus 2y plus 3z equals to b1. Second equation is 4y plus 5z equals to b2. Third is x plus 2y plus 6z equals to b3. Second part is x plus y plus 3z equals to b1, 5x plus 2y plus 6z equals to b2 and minus 2x minus y minus 3z equals to b3. C part is minus x plus 2y minus 5z equals to b1, 2x minus 4y plus 10z equals to b2 and third equation is x minus 2y plus 5z equals to b3. Part D is x plus 2y plus 5z equals to b1, 2x plus 3z equals to b2, x plus 4y minus 5z equals to b3. Okay, so let's go back and read this question carefully. So here S is the set of all column matrices b1, b2, b3, says that the following system of equation has at least one solution. So then which of the following system will have at least one solution for each b1, b2, b3? Okay, so first of all we need to find the set S, right? So what is the condition? Condition is that this system has at least one solution, right? So S is the set of all those b1, b2, b3 for which this system has at least one solution. Okay, so let's first form the set S. Okay, so let's solve this problem. So consider this system of linear equation which is given in the question. Okay, minus x plus 2y plus 5z is equals to b1, 2x minus 4y plus 3z is equals to b2, x minus 2y plus 2z is equals to b3. So write the augmented matrix for this system, so which is nothing but minus 1, 2, 5, 2 minus 4, 3, 1 minus 2, 2, little bit, b1, b2, b3. Okay, so now let's apply some row operation. For example, let's apply this transformation r2 plus 2 times r1, and r3 is r3 plus r1. Okay, so under this transformation, so let's see how this matrix gets reduced. Okay, so let's write it in the next page. Okay, so the first row there is no change, minus 1, 2, 5, b1. Now r2 is replaced with the r2 plus 2r1, so this is 0 and this is 0. 3 plus 10 is 13, b2 plus 2 b1. Okay, now this one is r3 plus r1, so 0 and 0, and it's 7, and b3 plus b1. Okay, now we need to reduce it further because so far we cannot say anything about the rank of these matrices. Okay, so now I will apply this r3 goes to r3 minus 7 by 13 r2, so minus 1, 2, 5, b1 0 0 13 b2 plus 2 b1, no change. Now here 0 0, this is 0, okay, this is 0, and then b3 plus b1 minus 7 by 13. Okay, so let me erase this. Okay, yeah, 7 by 13 r2, it's b2 plus 2 times b1. All right, okay, so now what do we get? We get minus, so this is equals to minus 1 2 5 b1 0 0 13 b2 plus 2 b1 and 0 0 0, and this is nothing but 13 b1 minus 13 b1 b3 plus 13 b1 minus 7 b2 minus 14 b1 divided by 13. So we get 6 minus b1 plus 13 b. Okay, let's write it in the next. So we get the following system: minus 1 2 5 b1 0 0 13 b2 plus 2 b1 0 0 0, and here we get minus b1, so minus b1 minus 7 b2 plus 13 b3 divided by 13. So given that the system has at least one solution, therefore minus b1 minus 7 b2 plus 13 b3 has to be 0. All right, then only the rank of augmented matrix will be same as the rank of A, because here the rank of A is 2, but we cannot say anything about the rank of A augmented B. So if this minus b1 minus 7 b2 plus 13 b3 is 0, then the rank of augmented matrix will also be 2. Okay, so this implies that 13 b3 is equals to b1 plus 7 b2. So this is the condition. So as set is the set of column matrix b1 b2 b3 belongs to R3 such that 13 b3 is equals to b1 plus 7 b2. Okay, so we have formed the S set. So now let's take the part A and see whether that system has at least one solution for all b1 b2 b3 from S. Okay, so the system is this: x plus 2y plus 3z is equals to b1 4y plus 5z is equals to b2, and x plus 2y plus 6z is equals to b3. So let's call the system 1. Okay, so write the augmented matrix of the system 1 2 3 b1 0 4 5 b2 1 2 6 b3. Okay, so let's reduce this. So what do? We'll apply the transformation R3. So we apply the R3 goes to R3 minus R1. Okay, so the first row is as it is, 1 2 3 b1, even second row is also 0 4 5 b2, and this is 0, this is 0, and this is 3, and this is b3 minus b1. So here rank of A augmented B is same as the rank of A, which is equals to 3, right? This implies that the system, because we already get the 3 non-zero rows, and then this matrix is also in the echelon form. This implies system 1 has unique solution for all b1 b2 b3. Okay, therefore in particular system 1 has at least one solution for all b1 b2 b3 belongs to S. Okay, so let's go to the second part, B, which is nothing but x plus y plus 3z is equals to b1 5x plus 2y plus 6z is equals to b2 minus 2x minus y minus 3z is equals to b3. Alright, so let's check whether this system has at least one solution for all b1 b2 b3 belonging to S. Let's solve the system 2. Okay, so write the augmented matrix for the system 1 1 3 5 2 6 minus 2 minus 1 minus 3 b1 b2 b3. Okay, so this, okay, so what we'll do is we'll do some row transformation. So first one is this b1, the transformation is r2 minus 5r1, so this is 0, 2 minus 10, 2 minus 5, 2 minus 5 is minus 3, 6 minus 15 is minus 9, b2 minus 5b1, 5b1. Okay, let me just write the r2 is r2 minus 5r1. Similarly, I'll take this operation, r3 is r3 plus 2r1 plus 2r1. sorry, we don't have a space here. Okay, r3 plus 2r1. So this becomes 0. Then minus 1 plus 2 becomes 1. Minus 3 plus 6 becomes 3. And b3 plus 2b1. Okay, so now we need to make these entries 0. All right, so the next time what we will do is we'll apply the transformation r3, which is replaced by r3 plus 1/3 r2. Okay, so let's see with this transformation. R3 elementary row operation, r3 as a r3 plus 1 3 r2. So this will reduce the system of equation further. So 1 1 3 b1, there is no change in the second row, 0 minus 3 minus 9, and a b2 minus 5 b1. And here if I multiply the row 2 by 1/3, we get 1 minus 1, which is, and add it to the third one, it's a 0, and 3 minus 3 is 0. Okay, and we have b3 plus 2b1 plus 1 by 3 b2 minus 5b1. Okay, so what do we get? We get 1 1 3 0 minus 3 minus 9 0 0 0. This is b1, this is b2 minus 5b1, and this is 6 minus 5, so b1 plus b2 plus 3b3 divided by 3. So this is the reduced system we get. Okay, so this system will have a solution only if b1 plus b2 plus 3b3 is equals to 0. So this implies that for system to have at least one solution, we should have one solution for each b1 b2 b3 belonging to S. We should have b1 plus b2 plus 3b3 is 0 for all b1 b2 b3 from S, because then only the rank of augmented matrix will be same as the rank of A, because rank of A here, if you see, it's a 2, and if b1 plus b2 plus 3b3 is 0, then the rank of augmented matrix will also be 2, and then there will be at least one solution. Okay, so that means this condition should be true. Okay, so but this condition does not hold. It's not true for all b1 b2 b3 belonging to S, because for example 611 belongs to S, because to be in S we should have that 13b3 is equals to b1 plus 7b2. So this is true, right? What is the condition for being in S? So 13b3 is equals to b1 plus 7b2. So definitely this is true, right? This point belongs to S, but let's call this condition 3. Condition 3 does not hold. So this means the system 2 does not have at least one solution, will not have at least one solution for each b1, b2, b3 belonging to S. Okay, so let's go to the part C, which is system is x plus 2y minus 5z is equals to b1 2x minus 4y plus 10z is equals to b2 x minus 2y plus 5z is equals to b3. Okay, so let's call this system, let's call the system 3. No, 3 we already used, so 4. Okay, let me erase this. Okay, so let's consider the augmented matrix for this system: minus 1 2 minus 5 2 minus 4 10 1 minus 2 5 b1 b2 b3. So let's reduce this. So we'll just take minus 1 to minus 5 and b1. We apply that r2 goes to r2 plus 2r1, r2 plus 2r1, we get 0, and here also we get 0, and here also we get 0, and then r3 plus r1 we get 0 0 0, and here b2 plus 2b1 and b3 plus b1. So what is the row operation we used? We used r2 plus 2r1 and r3 is r3 plus r1. So here this implies what? This implies rank of A is 1. So for this system, for to have at least one solution, we need both b2 plus 2b1 is 0 and b3 plus b1 is equals to 0. So both the condition should be true, but (611), as we discussed in the last part, belongs to S, does not satisfy both these conditions. Okay, therefore system 4 will not have at least one solution for all b1 b2 b3 belonging to S. Okay, so let's go to the last part, which is D, and here the system is given by x plus 2y plus 5z is equals to b1 2x plus 3z is equals to b2 x plus 4y plus, no, not plus, minus 5z is equals to b3. So we need to check whether this has at least one solution for all b1, b2, b3, for all b1, b2, b3 belong to S. Let's call the system 5. Okay, so let's write the augmented matrix of the system: 1 2 5 2 0 3 1 4 minus 5 b1 b2 b3, and then you just reduce it. So what we do is 1 2 5 b1, then we r2 minus, we apply r2 minus 2r1, so this is 0, this is minus 4, 3 minus 10 minus 7, and b2 minus 2b1. Okay, and then r3 minus r1, so 0, it's 2, and this is minus 10. All right, and b3 minus b1. Okay, so now next we'll just do the elementary row operation. So here let me just write it, what operation we used at r2 2r1 and r3 minus r1. Okay, so here we will use the operation r3 plus 1 by 2 r1, and then we get 1 2 5 b1 0 minus 4 minus 7 b2 minus 2 b1 and 0, this is 0. Okay, then minus 10 minus 7 minus 7 minus 10 minus 7 by 2, so it's minus 10 minus 7 by 2 is minus 27 by 2. Okay, and then b3 minus b1 plus 1 by 2 b2 minus 2 b1. Okay, so anyway, this system has at least one solution for all b1, b2, b3, because here we can say that rank of A is equals to rank of A augmented B is equals to 3 for all b1, b2, b3. So this implies that system 5 has at least one solution for all b1, b2, b3 belonging to S. Okay, so that means the system 1 and system 4 will have, part A and part 4, system defined in part A and part 4 has at least one solution for all b1, b2, b3, and part B, part C doesn't have it. Okay, so let's solve another problem. Question: let x, y, z be points with integer coordinates that is x, y, z are integer, satisfying the system of homogeneous equations (3x minus y minus z is equals to 0) minus 3x plus z equals to 0 minus 3x plus 2y plus z is equals to 0. Then how many such points? Satisfy x square plus y square plus z square less than equals to 100. Okay, so let's solve this. Okay, so here if you see, these are the system of homogeneous equations. So homogeneous system of equations has b which is 0. So here b is 0, 0, 0, b is 0 vector, and a is 3 minus 1 minus 1 minus 3 0 1 minus 3 2 1. So in this case, rank of A is always equals to the rank of augmented matrix AB. The reason is because B is 0 vector. Alright, so let's try to find the rank of A. So we have A, which is given by 3 minus 1 minus 1 minus 3 0 1 minus 3 2 1. Okay, then we just apply the row transformation, which is R2 is R2 plus R1, and R3 is R3 plus R1. So the first row is same. Okay, then this is 0, this is minus 1, and this is 0, this is 0, this is 1, and this is 0. Alright, so now let's reduce it further. Here we'll use the R3 as R3 plus R2. Then we'll have 3 minus 1 minus 1 0 minus 1 0 and 0 0 0. Alright, so here if you see, the rank of A is 2. Right, rank of A is equals to 2, which is less than 3. This implies system has infinitely many solutions. Okay, so let's take the reduced system of equation. So what is that? 3 minus 1 minus 1 0 minus 1 0 0 0 and x y z is equals to 0 0 0. Alright, and this gives us 3x minus y minus z is equals to 0 and y is equals to 0. Y is 0, this implies that z is equals to 3x. Alright, so this implies that if you take x as alpha, then alpha 0, 3 alpha, is that alpha integer, because we are interested in integer solution. Okay, is set of integer solution of system of equation. System of equations. Okay, so we need to find that how many such solutions satisfy the x square plus y square plus z square less than equals to 100. Okay, so for alpha 0 3 alpha to satisfy x square plus y square plus z square less than equals to 100. We have alpha square plus 9 alpha square less than equals to 100. This implies that 10 alpha square less than equals to 100. This implies alpha square less than equals to 10. Okay, given alpha is integer, okay, this implies alpha should belongs to -3, -2, -1, 0, 1, 2, 3. All right, then the integer solutions. Satisfying x square plus y square plus z square less than equals to 100 are given by zero 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 103 206 309 -1 0 -3 -2 0 -6 -3 0 -9. So this means total number of points. Total number of points is 7. Okay, so this is the final answer. Let's solve another question. So consider the following. Linear equations. Ax plus by plus cz is equals to 0. Bx plus cy plus az is equals to 0. Cx plus ay plus bz is equals to 0. Then if a plus b plus c not equals to 0 and a square plus b square plus c square is equals to ab plus bc plus ca, then show that the equations represent identical plane. Part 2. If a plus b plus c not equals to 0, a square plus b square plus c square is also not equals to ab plus bc plus CA. Then show that the equation represent planes meeting at a single point. Okay. The third part is if A plus B plus C is 0 and A square plus B square plus C square is equals to AB plus BC plus CA, show that equations represent the whole of R cube. Okay, so let's solve this problem. The part 1. Okay, so here A plus B plus C is not equals to 0 and A square plus B square plus C square is equals to AB plus BC plus CA. So this simply means that 2A square plus 2B square plus 2C square minus 2AB minus 2BC minus 2CA is 0. So this implies that A minus B whole square plus B minus C whole square plus C minus A whole square is 0, right? Okay, so this implies that because A minus B whole square, so this is the sum of three positive non-negative numbers, and the sum is 0. So this implies that each and individual term has to be 0. This implies that A minus B is 0, B minus C has to be 0, C minus A has to be 0. Alright, so this implies that A equals to B equals to C, and because A plus B plus C is not 0, so this is not equals to 0. Alright, so we obtain that this A is equals to B is equals to C. So this implies that equations represent the identical plane. Okay, so let's go to part 2. So in the part 2 we have A plus B plus C not equals to 0 and A square plus B square plus C square not equals to AB plus BC plus CA. Alright, okay, so here let's take this coefficient matrix A, which is nothing but A B C, B C A, C A B. All right. So what is the determinant of A? Determinant of A is nothing but A times BC minus A square minus B times B square minus AC plus C times AB minus C square. So this is nothing but 3ABC minus A cube minus B cube minus C cube. Alright. So as we know that A cube plus B cube plus C cube is equals to A plus B plus C into A square plus B square plus C square minus AB minus BC minus CA plus 3ABC. Alright, this is what we know. So this implies that determinant of A is equals to minus of A plus B plus C, A square plus B square plus C square minus AB minus BC minus CA. So given A plus B plus C is not 0 and A square plus B square plus C square is also not equals to AB plus BC plus CA, this implies that determinant of A is 0. So this implies that system of homogeneous equation, not 0, sorry, system of homogeneous equation will have a unique solution. And which is nothing but x is equals to 0, y is equals to 0, z is equals to 0. So the trivial solution is the only solution. So this implies that the planes are meeting. This implies that equations represent planes meeting at single point. Which is the 0, 0, 0. Okay. Alright. So let's go to third part. So what is the A plus B plus C is 0 and A square plus B square plus C square is equals to AB plus BC plus CA. So these are the two conditions. So as we did in the first part, A square plus B square plus C square is equals to AB plus BC plus CA gives us A is equals to B is equals to C. Okay, and this implies that A plus, in place of B I put A is 0. This implies that A is 0. This implies that A is equals to B is equals to C is equals to 0. So this implies that any x, y, z belongs to R cube will be the solution of system of equations. Okay, so this implies that equation represent the whole space. Whole of R3. So that's it. I will stop here. Okay, students, I will stop here now. This was the last lecture of this series. Thank you for attending these problem solving sessions. I hope you enjoyed them. I wish you good luck. Thank you.